All right, if everyone could please take their seats, I think we're going to get started with this session. So thanks everyone for making it this morning to our session on neurodevelopment. So I'm Jessica Huayi, this is Valerie Sinnor, and we'll be co-chairing this session today. I encourage you to use the app if you have any questions, but after the talk, we'll be taking one or two questions from the audience. So if you'd like to walk up to the mic, feel free to do so. So without further ado, I'll introduce our first speaker, who is Wenjie Hou, who will be talking to us about ADHD symptom trajectories, cortical thinning, and hippocampal expansion as neural signatures. Please take it away.
Good evening, everyone. I'm very glad to be here to present our recent work on exploring the neurodevelopmental mechanisms underlying the heterogeneity in ADHD symptom trajectories. The topic I will present today is ADHD symptom trajectories, cortical thinning, and hippocampal expansion as brain signatures. ADHD is one of the most common neurodevelopmental disorders, affecting approximately 5% of children and adolescents across the world. Meanwhile, ADHD symptom trajectories are highly heterogeneous, including the persistent, remitting, and emergent trajectories. ADHD is also highly dependent on neurodevelopmental process. The persistence, remission, emergence trajectories are closely related to dynamic development of the brain. Philip Shaw and his colleagues recently proposed developmental models for ADHD symptom trajectories. The convergence model suggests that symptom remission as brain gradually catching up to typical developing control. The cascading model suggests that the early symptoms may worsen brain structure and functional development, creating a virtuous circle. The carried forward model suggests that brain difference was set at childhood and the later symptoms just follow this pattern. These models provide a theoretical framework for us to understanding the neurodevelopmental mechanisms of ADHD symptom trajectories. However, they still have some limitation. First, the current model didn't cover the emergent individuals. The second, most previous studies use relatively small sample size and always use the cross-sectional design. Based on the previous study, we proposed 3 key questions of our present work. The first, are ADHD symptom trajectories associated with distinct behavior developmental profiles? The second, can we identify distinct brain signatures for each symptom trajectories? The third, can these brain signatures predict subsequent ADHD symptoms and generalize to other independent samples? The next is our definition of ADHD symptom trajectories. Here we use the ABCD study as the discovery cohort, the imaging dataset as the validation cohort. Following the literature, we defined the persistent, emergent, remitting, and control groups. The persistent group was defined as individuals who scored higher than the cutoff at both baseline 1 year and 2 year follow-up. The control group was defined as individuals who scored below the cutoff at both baseline 1 year and 2 year follow-up. The emergent group was defined as individuals who scored below the cutoff at baseline and higher than the cutoff at both 1 year and 2 year follow-up. The remitting group was defined as individuals who scored higher than the cutoff at baseline and below than the cutoff at both 1 year and 2 year follow-up. Next is the demographic information based on the ABCD study. Because ABCD study is a population-based cohorts, so most of them are divided into the control group, and the persistent group included 164 individuals, the remitting group included 141 individuals, and the emergent group included 76 individuals. Next, to answer the question 1, we use a cohort analysis to examine the between-group difference in functional and genetic profiles from baseline to 2 year follow-up. First, from the picture A, some proportion of the persistent, remitting, and emergent individuals was about 5%, which is consistent with epidemiological findings. Next, we found that the remitting group showed improvement in school performance, prosocial behavior, and sleep quality from baseline to 2 year follow-up, while the emergent individuals experienced deteriorations in school performance, social function, and sleep quality. Notably, we also found that the persistent group have the highest PIS for ADHD, and the following is the emergent individuals, remitting individuals, and control individuals. Next, to answer the question 2, we also used the ACOVA analysis to identify the brain signatures of distinct ADHD symptom trajectories. Here, the outcome is the relative change rate of neuroimaging features and defined as the follow-up 2 minus baseline and divided baseline. ACOVA analysis finds that as compared, ACOVA analysis showed that the persistent individuals may be characterized by accelerative synaptic pruning. As compared with the control group, the persistent group showed faster cortical thinning in 3 brain regions, including the right caudal frontal gyrus, the left and right superior frontal gyrus. The emergent group may be characterized by slower synaptic pruning. As compared with the control group, the emergent group showed less cortical thinning in the right caudal frontal gyrus, right insula, and right PCC. The remitting group may be characterized by brain decay development. As compared with the control group, the remitting group showed faster left hippocampal volumetric expansion. Next, we also tested longitudinal associations between brain signatures and ADHD symptom changes from baseline to 2-year follow-up. We found that in the remitting group, faster left hippocampal volumetric expansion was significantly associated with symptom decrease from baseline to 2-year follow-up in the remitting group. In the emergent group, we found that less cortical thinning in the right PCC was significantly associated with ADHD symptom increasing from baseline to 2-year follow-up. Next, to answer the question 3, among all the individuals who experienced high ADHD symptoms here, included the persistent remitting and the emergent individuals, we built 3 predictive models to predict ADHD symptoms, to predict subsequent ADHD symptoms at FU3. The clinical model included 6 variables, including the adolescent's age and sex, family income and parental education, PIS, and ADHD symptom score at baseline. The clinical longitudinal brain model additionally included 6 brain signatures identified above. The clinical baseline brain model additionally included the 6 brain signatures baseline value instead. From these 2 pictures, we can find that the predictive model included the 6 brain signatures identified above significantly outperformed than other models and significantly outperformed than predict other psychiatric symptoms at FU3. It means that the 6 brain signatures identified above have superiority and specificity in predicting subsequent ADHD symptoms at FU3. Finally, we also use imaging cohort to validate some of the findings identified in the ABCD study. First, the left hippocampal volumetric expansion was significantly associated with ADHD symptom decrease, and the predictive models included the 6 brain signatures identified in the ABCD study also showed also outperformed significantly than other models and could predict ADHD symptoms better. Okay. Sorry. Finally, we try to update the developmental models of ADHD symptom trajectories. Here, the emergent individuals should a divergent developmental trajectory with slower cortical thinning, leading to a shift from initially thinner to subsequent thinner cortical thickness as compared to controls. The persistent group was consistent with the cascading model, and the remitting group was consistent with the convergent model. Okay. Oh, sorry. Oh, thank you.
Thank you so so much for this really nice talk. I don't see any questions in the app, but if you'd like to ask a question, please feel free to walk up to the mic. I think people are just shy. Maybe we can get things started. So did you explore any potential sex or gender differences in your cohort, and if there was potential differences in this area on symptom trajectories, or is this something that you explored?
Yes. Sorry, can you repeat?
Yeah, so you looked at different symptom trajectories in your cohort. Were there any potential sex or gender differences in these symptom trajectories? Is this something that you looked at, or?
No, we didn't see the sex difference in the trajectory.
All right, I'll ask a question. Can you speculate on why you think the hippocampus is coming up as being so important for differentiating between these groups?
We validate hippocampal volumetric expansion was associated with ADHD symptom decrease both in ABCD study and imaging cohort. But to be honest, I think it's to some extent it's also a data-driven findings. I think it's just data-driven findings. Although there still have some literature reports that ADHD showed hippocampal development from childhood to adulthood. This finding was based on, I remember, it's Enigma ADHD. They published their work on lesson psychiatry, and yeah.
Thank you so much. Let's thank our speaker once again.